Hello, my name is David Mullins, Director of Technology with Nuvoda. In this video, we're going to play back a snippet from a recent live webinar. If you're interested in attending our live virtual events in the future, please follow us on LinkedIn. We look forward to hearing from you soon. Thanks for watching this introduction to the mob process. So I'll start with, what is the mob process and what does it stand for? It stands for Mobile Organic Biofilm, and kind of take you through the courses. So the aspect of this being a biofilm process, or really it's a hybrid process that has a carrier that's completely mobile, is pretty unique. You might be aware of other biofilm technologies out there where the biofilm is made to stay in a particular reactor unit, or perhaps it's even like a pure biofilm process like a trickling filter where it's truly staying in one place. This media is able to traverse the entire secondary treatment process. So you're looking at media going into the bioreactor, but then traveling into the clarifier, providing a significant sort of ballasting or settling aid in the clarifier, and then most of it being recycled back through the return activated sludge. For the portion that does normally then go to be wasted, as far as managing, an SRT or a mixed liquor concentration, that portion or that flow would go through what we call our biocarrier screen. Media is called biocarrier K. The K is because of the media, and I'll talk about that. The biocarrier then is returned back into the secondary process, and the flock solids, or sort of your traditional activated sludge, is wasted as it normally would. So this lends itself to a lot of benefits. There's not a whole lot of equipment changes required in the whole facility. By being completely mobile, we're not putting screens in the reactor or between reactors or anything like that. In terms of disruptions to operations on a retrofit, intercepting a WAS line is much more straightforward and simple to do with installing a screen there rather than having to screen the whole forward flow or something like that. It's also organic, so the media that we utilize, whereas most media out there are either sort of mineral or plastic or something like that, we utilize an organic media. So it's grown and harvested and produced by Nuvoda in North Carolina. You can see this year's crop doing very, very well between June and July. Just the speed at which it grows, it's a very viable crop for this application. The rate of growth, though, is sort of maybe a benefit for generating it, but what's really unique about the carrier, and I'll talk about this a little bit more, is just that it is organic. You're not putting plastic into a system, and it's got really nice properties that lend itself to high surface area and good settleability. And then it's, of course, a biofilm or a hybrid biofilm activated sludge process. So those individual pieces of biocarrier media, as they reside in the wastewater process over time, they are developing small colonies and then thicker and thicker biofilms over time. And what we typically see is something like 6 to 10 weeks, typical of developing a biofilm required to get sort of to a performance level. But then over time, even beyond that, for months and months, that biofilm matures. There's natural detachment, sometimes a little bit of detachment or sloughing that occurs. That's all managed and sort of controlled by controlling the overall SRT of the flock mixed liquor. And I'll talk a little bit about that as well. So a typical mob system, if you're looking at like a retrofit, you've got a bioreactor and a secondary clarifier, and then the RAS going around and the waste activated sludge. So simply modifying this, I mentioned it, but putting the WAS screen to retain that's how you sort of manage the overall SRT of the flock sludge by being able to waste. But you also then have this other SRT going on of the media, which is much, much longer. That media is returned to the return activated sludge or to the bioreactor, and then media is added to the bioreactor directly on the initial fill. It sort of exists in this closed loop. And then after media addition, that is how you operate. So there's not a constant media addition. You're maintaining this sort of robust population of biofilm, dense biofilm communities in your system. Just a little bit about the media. So the media itself, is often seen or delivered with these briquettes in the kind of in the upper right. That is sort of what it looks like for shipping only. Once it hits the wastewater, it sort of distributes back into finer particles. Those fine particles, being very small, provide a significant surface area. So this plant was chosen compared to various other organic options because of the high surface area and because of its specific gravity and settling characteristics. You wouldn't want to add something that would immediately drop out of the system. You also wouldn't want to add something that floats if it's going to go into a secondary clarifier. But in this case, the media is sort of the best of both worlds, providing a nice high surface area, and also in being organic, there's lots of benefits, but also the settleability is very favorable. If you look closely in the bottom left, you can see some of those surface area benefits. So just having all those ridges, nice areas for small, microbes to attach and resist any sort of hydrodynamic shear that's going on. We like to see some amount of shear in the system, so it does go through pumps, it goes through mixers, aeration. All of that is utilized to sort of control and ultimately sort of thin to medium thickness of biofilm, which you can see in the bottom right. So I always like to show the fun videos. So this one is the media going into the system. This is always a fun day because it's sort of the start. It's also the most where the day where you see the most action on site. So the bags are shipped, media is dropped into the basin. Typically, if you look at plastic carrier systems, those will require fill rates that are somewhere on the range of 40 to 60% of the bioreactor volume. So you'd have a whole lot of these bags going into the system. And for us, it's because it's providing a much higher specific surface area, there's much less overall media required, usually on a volumetric basis, closer to 1%, an order of magnitude less as a fraction of the overall volume. So yeah, those go into the system, takes about 15 to 30 minutes for those to disperse. Recommend adding slowly because it is going to the final clarifiers. We want complete mixing to happen, of course, so we're typically adding this to an aerobic zone to ensure that's all mixed up and all dispersed. And yeah, you're on your way. So, this is the first step, but there is time after this for that to develop. And then the rotary drum screen. So this is obviously an important piece of the scope. It's part of the overall MOB process and therefore part of the Nuvoda scope on a typical project. This is sort of engineered specifically for the application, utilizing a wedge wire drum. Ultimately, however, it's a relatively simple piece of equipment, not a whole lot of maintenance going on with these systems, perhaps a little bit of lubricant, depending on the model, having to change out some trunnion wheels from time to time, but you're just keeping an eye on essentially, making sure it's rotating, making sure it's not making a whole lot of noise. But essentially the RAS or the WAS comes into the screen, again, separates that flock, wastes that out like normally, and then you have your biofilm or your attached media, or what we call our mobile biofilms, retained by the screen and returned to the process. Didn't talk a whole lot about it yet, but by having two different biomasses, you've got a fixed film or attached growth biomass and a suspended biomass, you get the benefit of having sort of two different SRTs in the system. A shorter SRT with the suspended biomass, and then a longer SRT with the attached growth. And by having those two different SRTs, you have some interesting opportunities to select for slower growing organisms on the media, and then more of your faster growing, your ordinary heterotrophs, for example, in the flock. So there's different responsibilities with each item. This screen enables that possibility by creating a physical selector that's selecting between those two SRTs effectively. I just have another video here showing what the drum screen would look like on the inside. This is what it would look like, the media after it's sort of de-briquetted and sort of reintroduced into the system, traveling through the RAS and then again into the WAS. This is being retained on about day 1 or 2 of the system being in operation. So you see a pretty light color of the media itself. Over time, this will darken in color, which is indicative of biofilm growing on the media, essentially covering that with a nice film. So first case study we're going to talk to today is located in Reno, Nevada. It's the Truckee Meadows Water Reclamation Facility. So this is a 30 mgd AO process. So it's an anaerobic oxic process that traditionally would remove, in the secondary treatment, it would remove BOD and would also perform very well on biological phosphorus removal. They also do have nitrogen removal, and that's done in the tertiary treatment. So basically there's activated sludge, clarifier, and then tertiary steps where they actually provide nitrification, and then a separate step with denitrification. So they're very stringent limits on their phosphorus and overall nitrogen, driving this sort of complex plant layout. So there's a process flow diagram. So we put the mob process into that AO activated sludge zone with a few project goals. We wanted to nitrify. So remember, this is just for BOD removal normally. So we wanted to achieve, nitrification, demonstrate less than 1 milligram per liter with the mob process. Wanted to maintain that historically excellent biological phosphorus removal. Anything that's not removed biologically would need to be removed with chemical later down in the process. Improve the settleability. It's one of the key foundations of the mob process. And then as a bonus, if it's possible with that existing volume, wanted to achieve some additional TN removal in the bioreactor. And ultimately, this had the goal of a few different things, either eliminating or sort of reducing the reliance on those nitrification towers later on, and then reducing the methanol if we could get some denitrification. So this was done as a long study. It's been operating for several years now and has sort of been permanentized. But you can see here the process layout. They've got an anaerobic zone 1, 2, and 3. That's where they have that phosphorus release occurring. We added the media then to the 3-pass aerobic system, so 4, 5, and 6. And then later on in the study, and I'll talk through the graph, initially after we'd established nitrification, we also looked at that denitrification. And they put some mixers in, shut their aeration off, created a denitrification zone, playing around with a few different carbon sources to optimize that denitrification step. The drum screen is located over in a building. So coming from the clarifier, the RAS or the WAS would come to the drum screen, go to normal wasting, and the media was returned back here into cell 5. So looking at the overall performance here, we've had 3 different systems at this site. There's 1, 2, and 3. 1 and 2 can be sort of considered your control or operating as normal. And then the mob process was in system 3 and is currently in system 3. So you can see shortly after the media was installed, there was that acclimation phase, the 6 to 10 weeks. It was done in winter as well, so it's a little bit slower growth. But the nitrification sort of started to take hold. And once that took hold, you can see that the total inorganic nitrogen removal, which is your ammonia, nitrate, nitrite, all together, steadily increased, working through different steps to get to around 50 to 60%. So that represents pretty much complete nitrification, and then not quite, doing a whole lot on the denitrification side. But we think that the denitrification was either some combination of simultaneous nitrification, denitrification due to some lower DOs in the back zone, as well as potentially some denitrification happening in the blanket. So then when the denite was really sort of put into overdrive was when we added that denitrification zone. That created an anoxic environment with some additional carbon, where then they were able to push 70 to 80% plus on the overall total inorganic nitrogen removal. What's important to remember is this was all done in a system at about a 3 to 4 day SRT. And it was also done in a system that normally only removed phosphorus and BOD. By being able to intensify this existing volume to both nitrify and then denitrify, we showed a major improvement over the baseline performance of these other control systems. And then, later on, that meant less reliance on that tertiary nitrification tower and the tertiary denitrification process. And just talking through what the ammonia looked like in that same time. So, you see nitrification kicking in, realizing complete nitrification, and once we had it, we didn't lose it. So you can see it was looking really good for a long time. As we got a little bit later in the process, what we wanted to do is restabilize and focus less on just the nitrification, but stabilize the TN removal for some cost savings, and to stabilize the biological phosphorus removal, which I'll talk about now. So the next slide is going to talk about the phosphorus removal. But what's important to understand is that without the denitrification present, what we were doing was sending too much nitrate and nitrite back to the biological phosphorus removal. So there are several phases going on here. In the first phase, we had the startup and biofilm growth. So that, and this is now looking at effluent orthophosphorus on your y-axis. And in the phase where we were optimizing for nitrification, the denitrification really wasn't there. We're sending all that NOx back to the anaerobic selectors. And depending on the day or sort of different conditions and how much carbon was coming in and some different things, there was variability in the orthophosphorus in the effluent, getting as high as 2.5, but, averaging probably closer to 1.5, somewhere in that range while we're optimizing nitrification. So after getting through that phase, we proved to ourselves we had the nitrification. We added that denitrification zone. And once we did that, it was shocking how much it dropped. So we had a streak of 70 days in the optimizing the BNR where the orthophosphorus was non-detect coming out of that process. Had a little bit of a blip as a process upset with some different things that were going on at the plant on the solids handling and other things, but came right back and recovered quickly. So I think this is interesting and illustrative of how BNR works. That if you're trying to get phosphorus removal, you essentially also want your nitrogen to be removed as well if you're going to nitrify. Of course, before, if you're not nitrifying as well, if you have no care in the world for your ammonia or your nitrification in the particular process, BOD removal without nitrification is also going to be low in nitrate, that chemically bound oxygen that would otherwise disrupt the EBPR. But yeah, so I think looking into the future, this plant is going into a longer term study to look at the rest of the facility and how they're going to implement. It's clear that denitrification is a very important step that will need to be included if they're going to continue to nitrify in these bioreactors. And it appears that that's the direction that they're going to go. And just focusing in on that sort of very, very good period, specifically looking at the other systems that do very, very well with biological phosphorus removal. But again, those are just BOD removal only. You can see that the MOB process compared to system 1 and 2 was very, very low. So I think it highlights the potential of what is there. The study has been completed and now they're sort of in normal operation. And they've got some other operational methods that they utilize, such as intermittent mixing, some different things that really, really intensify their biological phosphorus removal. So looking at it overall, achieved the effluent ammonia less than 1 at 3 to 4 day SRT. Didn't talk about this much. We talked about, I think, in a previous presentation, but the SBI is improved in this system versus the others. Achieving that additional TN removal without having to add volume, but simply with a baffling or sort of utilizing is really characteristic of how you can, how intensification isn't just for maybe flow expansion, but can also be for permit changes or improvements to an existing facility. So if you have a facility where you may not be seeing a 25% increase in your flow over the next, 10, 15 years, but you are seeing total nitrogen or biological phosphorus required in your permits, this is something you could look at with small modifications to your bioreactor. Effluent total phosphorus, we talked mostly orthophosphorus, total phosphorus less than 0.3, and didn't mention too much of this, but the operational savings on methanol. So getting that total inorganic nitrogen removal of 80% plus, definitely has downstream effects, saving them significant chemical addition.